We today have 70% of the steel or iron that we make coming from coal and iron ore. Our challenge is going to be to look at some different ways of making it. These technologies, this circular route, using more hydrogen is what will get us to net zero in terms of our carbon emissions. But we don't want to stop here. We are also looking at processes where we can go directly from iron ore to iron without having any carbon, just using electricity. Some people look at all these technology developments as a cost, but I think it's an opportunity.
Hello and welcome to Futurising. My name's Tom Cheesewright and I'm an applied futurist, helping people around the world to see the future more clearly. No topic looms larger in my work than climate change and the move to net zero. In this series, we are looking at the role of the steel industry in this urgent transition. Steel production is responsible for a large share of greenhouse gases. But as you will hear, it's hard to see a transition to net zero without a major role for steel. So what is the answer? Through a series of conversations, we'll be exploring multiple facets of the future of steel in the context of a world facing a changing climate. Is there such a thing as green steel? What are the barriers to its production? And how do we ensure a just transition? If you're familiar with how steel has been made for many centuries, using fossil fuels as the energy input to turn iron ore into steel, it's hard to imagine how steel could ever be green. But technology advances apace, and there are always new options coming online. In this episode, I'm joined by Pinakin Chaubal, who leads new technology development for ArcelorMittal. Pinakin shares his deep knowledge and truly global perspective. We talk about the new technologies that ArcelorMittal is developing and deploying, the role of steel production in a circular economy, and why different technologies might be appropriate in different parts of the world. What comes across from Pinakin is a real excitement. This is an engineer who sees a great problem to be solved, perhaps the greatest. And it's a problem that has a very personal impact for Pinakin and for all of us. His motivation is absolutely clear. Hello, Pinakin. Welcome to the podcast. Let's start with an introduction. Tell us a bit about yourself and your role.
Okay, thanks, Tom. So my name is Pinakin Chaubal, and I'm originally from India, but I've been in the United States now for, over 40 years. And I'm a metallurgical engineer by background, and I decided I want to get to the real world, and why not steel? Because steel is probably one of the most exciting materials for a metallurgical engineer. So I joined the steel industry. This was in a company called Inland Steel, which at that time was one of, I would say, the leading companies in the United States in terms of its technology. And that was what drew me to the steel industry. And I started off working in the R&D department. Then I had the opportunity to go into operations, technology. We were acquired at that time, what was Ispat International, which was a company that Mr. Mittal had started. When ArcelorMittal was formed, the R&D organizations were all put together, and I was made responsible for what we call process R&D, which is looking at what are the technologies needed to improve our operations. 3 years ago, I was asked to take the role of the Chief Technology Officer for the company, and that's where I am today. So along with my team, we are working with all our sites across the globe, from mines, in fact, at times, to finished steel production, looking at improvements in technology, bringing in new technology, the guiding on what kind of investments have to be made to meet our future targets. And of course, decarbonization is right at the very top, because it represents probably the most intensive, large-scale transformation that one can ever imagine. And that's very exciting for all of us. I think to have a career where you're involved in this kind of a large-scale transformation.
You mentioned in that introduction there that the most important thing at the moment is decarbonising the process. What does the process look like today? I mean, how is steel made? How do we make steel at the moment, or at least how have we historically?
Yeah. So if we look there at steelmaking processes, so we can break it down. It's probably three key ways of making steel. Of course, there are some other minor ones, but one and two of them we start with iron ore. So you have iron ore, and you take coal and convert that into what we call coke, which is a densified hard form of coal. And we charge it to our blast furnaces and make molten ions. The molten iron at this stage has iron and carbon and some other elements in there, and it's at very high temperatures. It's about 1500 degrees centigrade. And then we blow some oxygen and we convert that into what we now call steel, right? So that's one route, so-called traditional integrated route. And then the second one, which we sometimes like to refer to as the mini-mill integrated route, is where the iron ore in different forms is converted to iron by gases, so natural gas being one. And so the iron is now in solid form. And then we take it to a furnace, we take it to the electric furnace to melt it, because you need energy to melt it. And that's the second route. And the third one is where we start with scrap, recycled scrap. So those are the three basic routes by which we make steel, or liquid steel first, and then we have to modify the composition to make it into solid form. And then after that, we process it to whatever final shape and properties we need.
It's quite a complex process. It's quite a carbon-intensive process, or at least has been historically. Why do we do it? Why is steel so important? Why has it been such an important material?
So if you look around you, sometimes you don't even realize how much steel is around you. It's embedded in the walls, so concrete walls. It's a very important material for construction. There are bridges, the cars that we drive, the appliances that we have at home. It's everywhere. And I even like to say that it's in us, because after all, hemoglobin contains iron, which is very important for us to live. But you look historically, there were iron ore formations which were easy to mine out, so to speak. Bog iron is a term you probably have heard. And when industrialization was going on, coal as a source of carbon, a source of fuel, was readily available. And when you put those two together, you are then able to make iron. And this is how making iron started. And it was a process which was very easy to scale up, because as people learned and were able to get iron, they found different uses for it. And that's why we today have probably in the world about 70% of the steel or iron that we make coming from coal and iron ore. And now our challenge is going to be to look at some different ways of making it.
You mentioned that we've always been making iron and steel for a long time. There's a lot of steel out there. And you mentioned that one of the processes for making steel is bringing in scrap. Is there not enough scrap out there for us to meet demand, to actually sort of recycle? Can we not recycle everything we've already made, all those buildings we tear down, all those cars that we scrap? Is that not enough to meet demand?
So there are two parts to the answer to your question, Tom. First of all, steel has a very long life. And maybe I should go back a little bit and say, we use the word steel, but it's just a generic term for a whole family of products that we make, our primary products that we make. And that's the beauty of steel for me, is that you can modify the properties by changing the chemistry a little bit, by changing how we process it. And so you've got steel that is soft, you've got steel that's very hard. And so it's probably one of the most exciting materials as far as I'm concerned. And so the thing is that there is of course, there's a finite life for every product that you make. But in the case of steel, if you look at what are the applications, you've got, for example, bridges, you've got buildings that are made, and these last for a very long, long time. So what you're calling scrap today that we are getting is from steel that was probably made 50, 60, 70 years ago. And at that time, the demand was far less than what it is today. And the demand for steel is going to keep growing. World population is growing. We are building more cities. We are spreading out to places where we never thought we would be living, right? So there is always going to be a lot less scrap than the demand for steel. And that difference has to be made from other ways of making steel and not just from scrap. So that's the first part of it. The second part also is that certain kinds of steels are requiring some very, very high-end properties. And in order to meet those properties, you can't always look at recycling, because recycled steel comes with all the other chemical elements that you added to make that particular steel. Yes, we can think in terms of trying to segregate the scrap and try to make sure that you have more pure scrap to meet the compositions, but that's not easy. That's difficult. So you put both these together, and it's clear to understand why we only will solve part of our steel making needs from scrap.
You talked about 3 methods of making steel there. How are those methods changing? What are we starting to do differently in terms of the production process?
So it's an interesting question. So if you look at the most important primary method of making steel, so the first step of the process is what we call the blast furnace. And a lot of times people come up to me and say, oh, but this looks very similar to what you had 50 years ago, 70 years ago. And I said, yes, that is true. And basically the concept is simple. You take the iron ore and you charge it to the top, and you take this coke and you charge it in the top, and you blow air, or you blow hot air, and then you get this liquid iron, which you'll process further. But that is, I would say, probably a very simple way of looking at it. We have made significant progress in terms of the control, in terms of the efficiency of the process. And just as an example, in the last probably about 30 to 40 years, we have decreased the amount of energy needed, or the amount of carbon needed to make 1 ton of steel, by a factor of 2. So that is a significant improvement.
In some ways, that's a reduction of waste, I guess. You're not producing anything that doesn't get used because you're ensuring the quality that comes out of there. What about in terms of the decarbonisation of the process? What technologies are starting to go in there today?
So the first part, of course, always is the most efficient way to run it, right? So this is one part, and we still have to keep working on it. We'll never give up on improving the efficiency of our processes. That's one thing. The second thing is we also produce a lot of gases. And a lot of the carbon that comes into the process is released as a gas. And those gases have to be reused. So in the earlier times, there was a lot of emphasis on using it to be an energy source. Because otherwise you would be burning coal, or you'd be burning natural gas, or nuclear reactors, whatever. And here you have this energy in the gas almost free for you, because you made the iron already. So that was the focus. Now the focus is, how are you going to make sure that this carbon that comes in does not escape out as a gas? And so our focus today is on looking at technology that will allow us to move away from that. So the main integrated route, the one where we have the blast furnace, their efficiency is the most important. Second part is, what can we do with the gases when they come out? So, for example, we are in our facility in Belgium. We will be ready to start up a process where we are going to take these gases and we're going to convert them into ethanol. And ethanol is a good starting compound for a huge range of organic compounds that we make. Eventually, it can go into plastics, it can go into fragrance, it can go into cosmetics, all kinds of applications. And at the end of the day, ethanol is ethanol. It doesn't matter where it came from.
I really like that idea of capturing the carbon, creating ethanol, and that ethanol going into a perfume. I mean, do you see other industries sort of feeding off the back of the outputs from the steel industry?
So on one hand, if we can take whatever carbon we are putting in the gas phase, we always will need hydrogen, by the way, for making this conversion. Then there is a whole range of organic compounds that we can make. So ethanol is our first, I would say, foray into this, so to speak. But we have been talking to others about making naphtha, and somebody said IPA, and I thought, of course, IPA, beer. So no, it's isopropyl alcohol. And these are all very important starting compounds for the petrochemical industry. Also, because the iron ore comes with other compounds like silica, which is sand, alumina, which we don't need for making iron, but it has to be processed. So we are also working very hard on making sure that all these non-steel products that get made along the way can be used in other industries. So some of our slags are used for road bedding material. Some are used for making cements. So there are various applications, rock wool, insulation. So the whole idea is that we have to be a fully circular facility or a production, have a production step, not just for the carbon, but for everything that we make.
What about alternatives to some of the fuel going into the steelmaking process?
So there is carbon coming from coal. So this coal is there. And so let's talk about the different, the three different routes, because in each of the routes, there's a different way to look at how to change the fuel. So in the integrated route, the blast furnace and the route, we first of all started using more coal directly, because when you look at it, the use of more coal directly reduced the net amount of coal that was coming in from coal in the coke. And also we were able to take out the carbon from what we can call not so clean burning fuels, because there are so-called heavy oils which are waste, and we used to use them in the blast furnaces. So we started to move away from that.
So rather than refining the coal into coke, you can actually use the coal directly, and that reduces the total amount you need.
Right. So we can't remove all the coke. So roughly about today, our best practices get us to about 50% of coal directly and 50% coal that's converted to coke and then into the furnace. Now, we can use natural gas. So natural gas has a lot of hydrogen built into it, so to speak. So that brings down the amount of carbon we are using directly in the furnace. We are also now starting to talk about using more and more hydrogen. So today, hydrogen is expensive compared to the other forms of fuels that we use in the blast furnace. But as the prices come down, we will start to use more and more hydrogen. So that's one way of reducing the amount of, let's say, fossil fuels that are coming in. The other route, where we take the iron ore and we convert it into solid iron, again, that is using natural gas. But there again, what happens is that we actually convert the natural gas into hydrogen first and then use it. So if hydrogen is directly available, we can use it directly. So we are starting to look into that. And then there is some amount of carbon that's needed in steel making. And here we are looking at, let's call it circular, what we call circular carbon. So one form of circular carbon is biochar. So it's taking agricultural wastes and then converting them into carbon and some other gases. And because the agricultural products, the trees and all the corn that you grow and the wheat and et cetera, are going to eventually use the CO2 in the atmosphere. The net CO2 generation is essentially brought to zero. So that's the other way we're looking at reducing the amount of, say, fossil carbon that we're using.
What's next? Because I mean, it sounds like there's a variety of different things you can do today and are doing today. Do you have a sort of an idea of the roadmap for future improvements in this process?
So when we look at the targets that have been set up to meet our, when I say our, I mean the planet's 1.5 degree centigrade target, which unfortunately it looks like the world is going to go beyond that. But nevertheless, we have to make every attempt to make sure that we can reach that target. So we have to do things now, and we have to move fast, right? Because as we were discussing before, Tom, there is going to be a need for producing steel from iron ore directly. And our estimates are even moving to 2050, 2070, we're looking at least about 50% of the world's steel requirement has to come from iron ore. There's just not enough scrap. So so the first thing to do is to look at what technologies can be adapted very quickly to move the needle, so to speak. And the first thing we are looking at doing, besides, of course, improving the efficiency, is moving away, where appropriate, from the blast furnace route to the DRI route. So DRI stands for direct reduced iron. And the reason we use that acronym, so to speak, is because you're taking iron ore in its solid form and converting it into solid iron in one step. And we have announced projects now in some parts of the world. We're going to start digging in the ground, so to speak, in Canada in the next month. So where we will shut down the blast furnaces eventually and move to DRI. Now, DRI, because, as I said, using natural gas, that cuts down the amount of carbon we are bringing in. That's the first step. And then when hydrogen becomes available, we will move over to hydrogen, therefore making that process quite green up to that stage. What is exciting is that we don't want to stop here. We are also looking at processes where we can go directly from iron ore to iron without having any carbon, just using electricity in a process we call EAF, electric arc furnace. And in this furnace, all the energy needed to melt the iron is basically coming from electricity. Of course, it requires electricity coming from renewables, and there is a strong emphasis now across the world, in fact, in terms of moving towards electricity, which is green. So that also aids us, right? So that is one direction that we are taking. At the same time, we are looking at accelerating the development of technologies in the blast furnace route also. So we are not really putting all our eggs, so to speak, in one basket. We realize that we have to meet intermediate goals before we get to net zero by 2050, which is a group target. And today's transformation and what we have laid out for the next 7 to 10 years requires us to have technologies that will reduce the carbon emissions from our current facilities. So others are doing it, but what we are going to put in place are state-of-the-art, very high efficiency, high productivity units. So that's going to be a big challenge. And then be ready to convert them into hydrogen. We are also, like I was discussing, the pilot plant that we have in Ghent, by taking the gases from the integrated route to make ethanol. We can look at taking also some of the carbon dioxide that's being produced from the DRI process also and convert that. So all the modular technologies that we are testing out at industrial scale will be key pieces of technology that's necessary to meet our intermediate goals. Before we come to the point of very large-scale hydrogen use, the electrolysis, and that's kind of the end game. The electrolysis, I say it's the end game. But intermediate, there are lots of technologies that we are developing which need to be installed in our facilities to make us meet our targets. The other direction is that for the processes where carbon is still coming out in the gas phase, we want to see how to utilize those gases. We want to capture the CO2, convert them into chemicals, which are not going to be burnt. And that's an important point. They're going to be made into plastics or other forms, which at the end of life, we can bring back in the blast furnace. So we can complete the circle, right? We don't let the carbon go out in the atmosphere. That's the key part. We know that these technologies, this so-called the circular route, using more hydrogen, is what will get us to fairly close to, I would say, net zero in terms of our carbon emissions. And these processes are in the early stage of development. And with all the excitement that's there, with all the attention that's being paid, I'm hoping that the development of these processes to industrialization is faster than what we have traditionally been used to.
That's things on the near horizon. Are there things that are live today, sort of, transformations that are live today? I mean, I guess partially it's that transition from blast furnace to DRI. That's an ongoing transition, is it?
It is a transition that we are just starting. We as a company do have a lot of DRI operations already, so we do have a lot of experience. But as I said, the scale at which we are going to do this, the size of the units that we are going to construct will be cutting edge, will be state of the art, leading the industry. And to build a plant needs 3 years. So we start today. In 3 years from now, our first of this transition will be, you can see it in operation.
I'd like to do that. And in terms of the carbon capture technologies, where are they at today in terms of deployment?
So in terms of carbon capture technology, the ethanol production unit that we're going to start up in Kent, actually the first part of it is a carbon capture technology. And then we go and process. So we are going to already start having carbon capture now. We have a facility in Mexico where we are making DRI, where we capture the carbon. So we know how to run, or we will know soon how to run facilities for carbon capture. But what is the challenge? The challenge in carbon capture, so far in the world, people have been doing what we can call post-combustion capture. So it means, for the example, at the end of a power plant where all the gases have been burned. The challenge is pre-combustion. So where you have some carbon monoxide still there, you have some hydrogen still there, you have some other chemicals which can, let me say, poison the traditional process. So we are developing technologies and looking at pre-combustion carbon capture. And we are about to start a pilot plant in our facility in Dunkirk. We also will be very soon announcing an agreement with an engineering company to install pilot facilities in 3-4 of our different locations, all with the idea of being able to move to install carbon capture technologies and, where appropriate, either go to converting that into a chemical or looking at storage.
I really like that point about things coming back into the process as well. If you've got putting plastics out there, which has got a load of carbon and hydrogen in it, then actually feeding it back into the process when you're making steel as well. There's a potentially, I guess, at those temperatures, quite a clean way of disposing some of those materials.
Absolutely. So in the blast furnace right now, because when we carry out the combustion, we are reaching temperatures in excess of 2,000 degrees centigrade, we can burn out, so to speak, everything that's there. So even the nasties, so to speak, that are there in plastics, sometimes plastics have some other elements that have to be added to give it the right properties, they can be burnt out. So a problem with municipal incinerators is that they create all this waste, gases and waste compounds because they were operating at much lower temperatures. So the blast furnace actually is a more efficient way to convert these kinds of materials, waste materials, into a cleaner form. But moving forward, because as we said, we are decreasing the number of blast furnaces that we will have. But what we will do is we are also working on technologies which are called torrefaction. So torrefaction basically is heating in the absence of air. And so you can torrefy agricultural waste, you can torrefy wood, you can look at torrefying plastics. So that's the way in the future we're going to take these materials at the end of life and convert them into carbon. So that solid carbon can be used, and then convert them into gases and fuels, which we'll use again in our own facilities, and thus complete the loop.
And where's torrefaction at in terms of deployment? Where's that today?
So in our plant in Ghent, in Belgium, we are installing one reactor, and we will install a second reactor for torrefaction. And in this particular case, we will use waste wood. So today, waste wood is probably the most, well, this is that classification of wood, which even if it is waste, it has a lot of paint, varnishes, and all in that, and it is not easy to just put out in the open and let it be in the air, in the open air, so to speak. So the first reactor we should be starting up early part of next year, and what we will produce from this process, it's nicknamed Torero, coming from the torrefaction process, is some gases. So, and the biogases will then be used for the torrefaction process itself, and also in the adjoining center plant that we have. And the char that is produced will be used in the blast furnaces to replace fossil carbon. Now, the interesting thing is that this torrefaction process can be tweaked to use other materials. So we can use it for converting plastics, for example. So other end-of-life organic compounds to char and bio oil and biogases, which we can then use. So we really are, I would say, running pilot facilities or starting up pilot facility in the next 6 months or so to develop all these modules that we were talking about. So it fits well in Ghent, but then we can take the Torero process and maybe move it to a place where we have an electric furnace where we need some carbon. So that's the whole idea of developing these technologies and taking them to fit into any other process stream that we have anywhere in the world.
And are you looking beyond sort of the boundaries of the organization, looking at what's going on elsewhere and looking at other projects for whether it's actually the process itself or what happens to what comes out of the process? I think, are you looking at investments in other companies who are starting to develop some of these technologies?
So we realize that we are not going to be able to solve this all by ourselves. There are smart people everywhere. And there are a lot of what I can call enabling technologies. For example, production of hydrogen. If hydrogen can be produced in large quantities at the right price, it benefits us, but it benefits a lot of other companies also. So it makes sense in those cases to say, okay, let's look at companies that are in that space, those who are in the forefront of the new hydrogen production technologies, and let's engage with them. So the fund that we have set up, this XCarb Innovation or Investment Fund, is looking at targeting these kinds of companies who are in the so-called enabling space. And we will invest in them. We will work with them to see how we can adopt their technology when it's ready.
Is there a standard vision for what a future plant looks like, or is there some sort of variation? I'm just thinking about sort of supply chains here, and you mentioned renewable energy. Clearly, there's going to be different availability of renewable energy in different places. So do you have to have a slightly different vision for different plants around the world?
Indeed, that is correct. Because geographical locations will drive what alternate routes will make sense. So what works in Europe, for example, may not be 100% cut and paste in North America or South America. Or we have plants in Ukraine and Kazakhstan also. So our focus is to look at all the modular technologies that are needed and bring each of those modules to industrial maturity. And then we can, like a jigsaw puzzle, go to each site and say, okay, this piece and this piece and this piece will make sense to decarbonize. The fastest, at the lowest costs, best efficiency, and be able to meet the because at the end of the day, we have to make the targeted product. So as we were discussing, steel has a whole range of different chemistries. So depending on what products are made, we may be looking at different technologies to decarbonize.
Very cool. So given this sort of package of developments, we've got things on the sort of upstream and downstream and the process itself. What do you think a steel plant in 2050 might look like? We talked about these new technologies maybe coming on stream in the 2030s. If we push out to 2050, what does it look like by then?
It's an interesting question. So I'm going to sort of move away from saying that any of the current technologies are what we are going to have. I know that 2050 we certainly will have fully decarbonized ways of making steel with our current facilities. But if I really look way out in the future, what do we really want? The first thing is we want to be able to walk into a shop floor and see no dust, no dirt, no noise. We want to be able to go from the time, let's say you tell me that you need so many tons of this kind of steel, giving it to you in less than a week, for example. Today, the whole chain may take 3 to 6 months. A facility where you can maybe sit there and have your dinner, all right? And not be worried that you're going to be disturbed by the noise or the dust or the heat. That's what I would envisage.
I like the idea of a candlelit dinner there, and the gentleman wearing the aftershave made from the off gases from the process.
Why not?
My last question, and I'm interested in what the motivation is. You're clearly excited by the technology. What's driving you through this process to keep making these changes, to look at these different technologies? What's your sort of personal motivation?
So, of course, as an engineer, there's always the scientific curiosity and wanting to do new things. That's what engineers want to do, right? We get tired of the same old, right? But maybe I'll go back. So when I started my career, I had a colleague, and his wife is a physician. And she was practicing and I started in Chicago. So she was practicing on the north side of Chicago. And because the steel mills were on the south side, they finally moved. And then she started practicing on the south side. And the first thing she told me is that I cannot believe the number of patients that I see who have issues associated with the chemicals that are coming out of the steel plant. And it's, you're talking of 60 kilometers. And it was so clear. So I think from that time, all of us started becoming conscious that we have to find a way to start cleaning up. And first step, of course, was you want to make sure that there is no dust coming out. You want to make sure that the chemicals are not being allowed into either the air or the water or even in the soil. So those kinds of developments took place. Now our challenge is to make sure that we have a place to live in where we can walk safely, the kids can grow up and play. So I think the steel industry, it is so embedded in the culture, in the society of any particular country, must really contribute to making sure that the place that we operate in is safe, the place that we operate in is clean. When we were kids, we used to run around under blue skies and breathe clean air. That's what we need to have moving forward. So that's what really drives me now. And some people maybe look at all these technology developments as a cost, but I think it's an opportunity.
That's great. Thank you, Pinakin.
Thank you, Tom.